Do you know how to find equilibrium point in an array? If your answer is no, then this video is for you. Hi guys, I Aziz welcome you to CoedMaster, and in this video I am going to talk about how to find equilibrium point in a given array. So please watch this video till the end. So let's get started. Alright guys, let's begin this video with this problem. The problem is given as we are given an array and we have to find if this array has equilibrium point or not. Okay, we understood that we are given an array and we have to find equilibrium point. If it exists, then we have to return true, and if it doesn't exist, we have to simply return false. But the question over here is, what does it mean by equilibrium point? So let me show you. So let's consider this is the given array. So equilibrium point is a point in an array such that sum of all the elements to the left of it is exactly equal to sum of all the elements to the right of it. Okay? And you can see here that these are the elements to the left of it and these are the elements to the right of it. And if we compute the sum of these elements and these elements, we get the sum exactly equal. Okay? So this is what the equilibrium point means. So guys, now you understood the problem and what does it mean by equilibrium point. So moving on, let's understand this problem with few examples. So let's see this first example. Here the array is given as 1, 6, 3, 5, 2, and this array has equilibrium point, and that point is element 3, because if you compute the sum of all the elements to its left, 6 plus 1 is 7, and if you compute all the elements to its right, that is 5 plus 2, you get this 7 as the sum. 6 plus 1 is equal to 7 and 5 plus 2 is also equal to 7. That is why the output of this input is true. Let's see this next example. Here the array is given as 3, 1 and minus 1, and in this array also there is a equilibrium point, and that point is at position 1, that is 3. The reason is simple. On the left side of 3 there are no elements, so the sum of elements to its left is 0, and sum of elements to its right is also 0, because 1 and minus 1 cancel out each other and it becomes 0. So that is why the output of this input is true. Let's see the next example. In next example, the array is given as 1, 2, 3, and if you observe this array, there is no equilibrium point in this array, because if you consider 1, then on the left of 1 the sum of all the elements is 0, but on the right the sum of elements is 5. If you consider 2, on the left side the sum of element is 1 and on the right side the sum of element is 3. And if we consider 3, on the left of it the sum of elements is 3 and on the right of it there are no elements, so the sum becomes 0. So you can see that there is no equilibrium point in this array. So that is why the output of this array is false. So guys, now you have good understanding of this problem and you also know that what is meant by equilibrium point. So how we are going to solve this problem? So here is the first and the basic approach to solve this problem. And what we do in this approach, we are going to run a loop from 0 to n-1. And the reason is simple, to pick one element at a time. And then once we pick one element, we go to left of that element and find the sum of all the elements. Similarly, we go to right of that element and find sum of all the elements. And then we simply compare both the sums. If we found that the sum are equal, then we say that this is an equilibrium point. If we do not found any of the element whose left sum and right sum is equal, then we simply return false. So this is the basic idea of this approach. So although this is a basic idea to solve this problem, but we are concerned about the time and space complexity, right? Because we want efficient approach to solve this problem. So let's see how much time this approach is going to take. So in the first step, we are running a loop to pick one element at a time, okay? And in each iteration of this loop, we are running two loops. First loop to find the sum of left elements and second loop to find the sum of right elements. It means for each iteration of outer loop, we are running inner loop n times, okay? And obviously you can see here that the outer loop is running n times and inner loop also runs n times. Let's say for element 3, we have to go to left of it and we have to run loop 2 times. Then we have to go to right of it and we have to run loop 2 times, and 2 plus 2 is 4. So it is around 4 plus 1 5 like this, and there are 5 elements you can see here. Okay, so in worst case we can say that the time complexity of this approach is going to be big of n square, right? Because these are nested loops. And what about space complexity? We are not using any extra space, we are just running 2 loops. Okay, so that is why the space complexity is going to be theta of 1. So overall, if you look at this approach took big of n square to solve this problem and constant space. But I don't think this is a efficient approach to solve this problem. We have many ways to optimize this approach, and we will see it in a bit. So this is the first approach to solve this problem. Now let's move on to next approach that is little bit better approach than the previous approach to solve this problem. And in this approach we are going to use the concept of prefix sum. Yes, you heard that right. Let me show you how prefix sum help us in solving this problem. So first of all, in this approach we are going to compute the prefix sum of all the numbers. And if you remember from the prefix sum video, we compute prefix sum to find the sum up to particular element, right? For example, if you consider 1, then there are no elements to the left of 1, so the prefix sum is 1. Then if we consider 6, there are 2 elements, 1 and 6. So up to 6, the sum of left elements are 1 plus 6, that is 7. So this is how we compute prefix sum. And we know that how to compute the prefix sum. Okay. Now next step is compute the suffix sum. And what is suffix sum? It is exactly same as prefix sum. The only difference between prefix sum and suffix sum is we start computing the sum from the right of the array instead of the left of the array. In prefix sum, we traverse array from left to right, but in suffix sum, we traverse array from right to left. And in each iteration, we compute the sum. Okay. So for example, the suffix sum of 2 is 2 because there are no elements on the right of it. Suffix sum of 5 is 5 plus 2, that is 7. Up to this point, this sum is 7. And we can see that 5 plus 2 is 7. And for this point, this sum is going to be previous sum plus this element. So 7 plus 3 is equal to 10. So up to this point, the sum of this array is 10. You can see that 5 plus 3 plus 2, that is equal to 10. So far we have computed prefix sum and suffix sum. And now what we are going to do? We are going to traverse this array from first element to last element, except the corner elements. I will talk about the corner elements in a bit. So in each iteration, we check if prefix sum of I minus 1 is equal to suffix sum of I plus 2 or not. And if both of these are equal, then we simply say this is a equilibrium point. Let me show you how. So let's say the element is 6. Now if we consider this position, the prefix sum before this element is 1, okay, because we are considering I minus 1. And the suffix sum after this index is 10, and 1 is not equal to 10. So we skip this step, right? And how is it working? Because before 6, the sum is 1, we already know. And after 6, we can see that the sum is 10, okay? And we can get it from suffix sum. Now moving on to next element, that is 3. Now again we are going to compute if prefix sum of I minus 1 is equal to suffix sum of I plus 2 or not, okay? And we can see that prefix sum of I minus 1 means 3 I minus 1 of 3, that is equal to 6 plus 1, that is 7. So we get this from this prefix sum array. And what about suffix sum I plus 1? And suffix sum I plus 1 is 7. You can see here, this is our ith index and I plus 1 is this. So now you can see that the suffix sum is 7 and the prefix sum is also 7, right? So this is the case where we can say that this is an equilibrium point. Now what about the corner elements? So what happens in corner elements? If the element is first, then we know that there are no elements to the left of it. So we simply have to find the suffix sum of I plus 1. So in case of 1, we have to find the sum of all the elements to the right of it, okay? And the index for finding the right sum is I plus 1, right? So this is about the first element. Now what about the last element? So in last element, we know that there are no elements to the right of it. So we simply check if the prefix sum of I minus 1 is equal to 0 or not. If I consider 2, on the right side of the 2 there are no elements, so the sum is 0 obviously. So we check the prefix sum of I minus 1, means before this element what is the exact sum, and exact sum is 15. So it means this is also not a equilibrium point. So as you can see that this is a better approach than previous approach to solve this problem, and we have successfully optimized the previous approach to some extent. So do you see guys what is happening here? We are first computing the prefix sum, and for computing the prefix sum we need extra array, and we have to traverse from first element to last element. Okay, and again to compute the suffix sum we need one extra space, one extra array to compute the suffix sum, and we have to traverse again from 0 to last element. Okay, and then to find if this array has equilibrium point or not, again we have to run a loop from first element to last element. So ultimately we are running 3 loops here, and we are also taking n space to store the suffix and the prefix sum. So we can say that the overall time complexity of this approach is going to be big of n in worst case, and space complexity also big of n, because we are taking space to store prefix sum and suffix sum. So guys, I hope you understood this approach better. But you know guys, we still have one way to optimize this approach, and you will be stunned to know that we can solve this problem in big of n time complexity and theta of 1 constant space. Well, let me show you the final and the efficient approach to solve this problem. So this is the efficient approach to solve this problem. And what is the idea actually? First we are going to compute the right sum of the array. And if we consider this array, this right sum of this array is 17, because 1 plus 6 plus 3 plus 5 plus 2 is equal to 17. And then we are going to traverse this array from left to right. And while traversing, we compute left sum using right sum for each element. This is really interesting guys. We can compute left sum using right sum. So this means we do not have to compute left sum at all. And how we are going to compute left sum? Let me show you. So let's consider this element 1. We know that the left sum of this array is 0 because there are no elements present to the left of this element. And we know that the right sum is 17. So how to compute the right sum of this element? It's really simple. We just have to do 17 minus 1, that is equal to 16. And 16 is going to be its right sum. As simple as that. And what about 6? We again take the previous right sum, that is 16, and subtract 6 from it. We get 10, and this is going to be the right sum of 6. And this is how we are going to compute left sum using right sum. Okay guys, now you understood the basic idea of this. Let me show you how it's going to work. So what we do basically, we initialize two variables, left sum is equal to 0 and right sum is 17, and we have already calculated this before. So we begin our loop with the first element, okay, and first element is 1, and we know that the left sum of first element is 0, okay. Then we compute the right sum. So right sum is going to be 17 minus 1, 1 is the number itself, is equal to 16, and then we compare both the sum, and we see that this time the sum is different, so we ignore this case. Then we move to the next element, that is 6, and again we are going to compute left sum, that is equal to previous left sum plus 1. Right, obviously for 6 the left sum is 1, so it comes out to be 1, and the right sum is going to be 16, the previous right sum minus the element itself, it's going to be 10. Again we are going to compare 1 with 10, and we again get different values, so we ignore this case. Then in next iteration we go to element 3, and again we are going to compute left sum, that is equal to previous left sum plus 6. You can see that the left sum of 3 is 1 plus 6, it comes out to be 7, and we compute right sum as previous right sum minus the element itself, it's going to be 7, and again we are going to compare left sum and right sum, and this time you can see that both the sums are equal. Here we can say that this point is the equilibrium point of this array. So guys, this is the entire process we are going to use to solve this problem. So this is much better than the previous approach. The reason is simple. We are not using any extra array, and we are simply traversing array only 2 times. So I hope you understood this approach. Now this is enough of the theory. Let's move on and see the implementation of this efficient approach. So here you can see that we have a function, equilibrium point exists, and this function is taking arrays input. Initially we are initializing two variables, left sum and right sum, and then we are running a loop to calculate the right sum. This is simple for loop, okay? And then we are again going to run a loop to pick all the elements one by one. First we are going to compute the right sum of that particular element, and then we are comparing if left sum is equal to right sum or not. If it is equal, we immediately return true. If it is not equal, then we are computing the left sum of that element so that we can use it in the next iteration. And if we do not find any equilibrium point, then in the last we are simply returning false. So this is all about the function. Now let's quickly dry run this code and see how it works. So the array is given as 1, 6, 3, 5, 2. We initialize left sum is equal to 0, right sum is equal to 70. So far so clear, okay? And we compute the right sum using this for loop, right? This one. After this for loop, the next loop begins. In first iteration, the value of j is 0. So first we compute the right sum, that is equal to 17 minus 1, that is equal to 16. And we check if right sum is equal to left sum or not. 16 is not equal to 0. So we do not do anything, okay? And then we simply compute the left sum. Left sum is equal to left sum plus ARR of 0, that is 1. So left sum become 1 and right sum becomes 16. Moving to next iteration. In this iteration, the value of j becomes 1. We compute right sum, that is equal to previous right sum minus ARR of j, that is 6. 16 minus 6 is equal to 10. And we compare. And here also both the sum are different. So we simply compute left sum, that is equal to 1 plus 6 is equal to 7. Okay. Then we move to next iteration where value of j is equal to 2. Here we compute right sum, that is equal to 10 minus 3, that is equal to 7. And this time if we compare left sum and right sum, it comes out to be exactly same. So at this point we simply return true. And we say that, okay, this is the equilibrium point in this given array. Okay. So this is why the output of this array is true. So guys, you can see that this approach has done pretty much good job, and we have to say this. And we have also successfully reduced the time complexity to big of n. Because you can see here we are running two loops n times. This loop runs n times and this loop also runs 2 times. And these loops are not a nested loop. These are subsequent loop. So the overall time complexity is going to be 2n. And in asymptotic analysis, we generally do not care about constant. So we remove the 2 and it comes out to be big of n. And space complexity comes out to be theta of 1. So overall, this approach took big of n time complexity and theta of 1 constant space to solve this problem. So guys, if you compare the time complexity of this approach with the first approach we had discussed, the time complexity of that approach is big of n square. And you can see that we have drastically reduced the time complexity from n to n square. And this time complexity is considerably way larger than this time complexity, because this time complexity belongs to the class of linear order of growth, and this time complexity belongs to the class of quadratic order of growth. So I hope this approach is clear to you. So on this note, let's end this video. So guys, if you learned something valuable out of this video, then hit the like button and subscribe to this channel. And also do not forget to click the bell icon so that you never miss the upcoming videos. So this is all from my side. Thanks for watching and see you in the next video.